So we've looked at a number of different derivative rules. One is the power rule. We've also looked at the product rule, the quotient rule, and a bunch of trig rules. But one thing we haven't considered yet until today is what to do with y equals the natural log of x. A number rule yet that will help us with this. And so if you were to find the derivative of this by typing this in, you'll get a sense of what's going on with this derivative. So this is math 8, or n derive, and if we let y1 equal this, we want to have the function ln x, comma x, so we're going to take its derivative with respect to x, starting at some x value and ending at some x value. If you look at the table and start your table at 1, you're going to see something like this. And what you should notice is that y prime in every case is just the reciprocal of x. It's just noticing this goes to the rule, the derivative of the natural log of x simply equals 1 over x. And this is true as long as x is greater than 0. And the reason x has to be greater than 0 is because in a logarithm, the argument, in this case x, has to be greater than 0. Now, our argument isn't always as simple as x. It could be something else, and that something else we'll just state broadly as u, like we have in other cases. And then all we're doing is employing the chain rule, where the derivative would be 1 over u times the derivative of u with respect to x. And again, this is true as long as u is greater than 0 for the same reason as given above. Right. Finally, we could be looking at the derivative of the natural log of the absolute value of u. And nothing really changes in this case. It's still 1 over u times by the chain rule du dx. But this, in this one case, since the argument is the absolute value of whatever u is, the only thing that has to be true is that u can't equal 0. Right? So we're going to use the chain rule, and it's always 1 over the argument times the derivative of the argument. Let's look at a few examples. If y equals the natural log of 4x, what's the derivative? Well, y prime would simply be 1 over the argument, 1 over 4x, times 4 in this case, or simply 4 over 4x, which is 1 over x. Alright, what about if y equals x squared minus 3, the natural log of x squared minus 3. Well, y prime is 1 over the argument, so x squared minus 3, times by the chain rule, the derivative of the argument, in this case 2x. Or if we simplify it down even further, we would get 2x over x squared minus 3. Let's look at another example. What if y equals the natural log of 3x squared minus 5x plus 8? Well, the derivative of all natural logs is 1 over the argument, so 3x squared minus 5x plus 8 times by the chain rule. In this case, it'll be 6x minus 5, or altogether 6x minus 5 over 3x squared minus 5x plus 8. Right, now something to notice is, and start thinking about in terms of integration, is the relationship between numerator and denominator, and when you might notice some things. The final example of this type, if y equals the natural log of the square root of x, well, y prime, again, by following the chain rule, 1 over the square root of x times, this would be 1/2 x to the negative 1/2. And cleaning all of this up, y prime would be 1 over 2x. Now let's consider some other derivatives that happen to have natural log in them, but that doesn't necessarily mean we'll be using the natural log rule at all or even exclusively. Y equals x squared times the natural log of x. Well, what I see here is the product rule. So y prime is the derivative of the first times the second plus the first function times the derivative of the second. And if we simplify this down, we've got 2x times the natural log of x plus x. And something to notice with something like this is the possibility of factoring, especially if we needed to take this further. This would be x times 2 natural log of x plus 1. Another problem of this type, y equals the natural log of x over x. Well, here I happen to see the quotient rule. So y prime equals 1 over x times x minus 1 times the natural log of x all over x squared. And simplifying this down, we've got 1 minus the natural log of x over x squared. Another problem of this type, if y equals x over the natural log of x. Again, quotient rule we might apply. So this would be 1 times the natural log of x minus 1 over x times x all over the quantity, the natural log of x squared. And cleaning this up a bit, we'd have the natural log of x minus 1 over the quantity, the natural log of x squared. And you might consider writing this as 1 over the natural log of x minus 1 over the natural log of x quantity squared. Doesn't have to be this way, but something worth noticing because sometimes it's beneficial. Next example, if y equals the natural log of x to the 5th power, what I see here is the chain rule. This would be 5 times the natural log of x to the 4th times 1 over x. Or cleaning this up perhaps, 5 times the natural log of x to the 4th all over x. And again, we can start seeing all sorts of different things involved in this. Y equals the square root of the quantity, the natural log of x. Recall that this is the same thing as the natural log of x to the 1/2 power. So, by the power rule, we would have 1/2 times the natural log of x, the whole thing to the negative 1/2, times by the chain rule, the derivative of the inside. And we might consider cleaning this up a bit to be 1 over 2x times the natural log of x to the 1/2. Another problem, if y equals the cosine of the natural log of x, well, the derivative of cosine is negative sine of the natural log of x by the chain rule times 1 over x. And cleaning this up, negative sine of the natural log of x over x. If y equals the natural log of the cosine of x, well, y prime would be 1 over the cosine of x times by the chain rule the negative sine of x, and this would simplify down to the negative tangent of x. Finally, let's consider y equals the natural log of the natural log of x. Well, this would be 1 over the natural log of x times by the chain rule 1 over x, and cleaning up, this would be 1 over x natural log of x. Again, we're just paying attention to a bunch of different things. In part 2 of this lecture, we will consider some more difficult natural logarithmic derivatives and applications.